Good morning to one and all. In today's lecture, we will discuss about the pulse modulation. In the previous lecture, we discussed about the continuous wave modulation in which we use the parameters like amplitude, frequency and phase of a sinusoidal carrier wave is varied continuously in accordance with the message signal. Now, today we will discuss about the pulse modulation. In pulse modulation, we use parameters such as amplitude, duration or position of a pulse train is varied in accordance with the message signal, then the process is known as pulse modulation. Pulse modulation are of two types, analog pulse modulation and digital pulse modulation. In both cases, periodic pulse train is used as a carrier wave. So, in analog pulse modulation, some characteristic feature each pulse like amplitude, duration or position is varied in continuous manner in accordance with the corresponding sample value of message signal, or we can say that information is transmitted in analog form, but while in digital pulse modulation the message signal is represented in a form that is discrete and in both time and amplitude. So in analog modulation we use sampling process, while in digital modulation we use sampling as well as quantization process. Coming on to the next point, that is information is transmitted in analog form but transmission take place at discrete times, that is for continuous wave process. While in digital, the transmission in digital form as a sequence of coded pulses, no continuous wave process. For example of analog is PAM, that is pulse amplitude modulation, and PPM, that is pulse position modulation. Coming on to the example of digital, first one is PCM, that is your pulse code modulation, second DM, delta modulation, and third one is DPCM, differential pulse code modulation. Now coming on to the advantages of digitalization of analog sources and digital system. First point, digital systems are less sensitive to noise than analog. Second, with digital system it is easier to integrate different services, for example video soundtrack, into the same transmission scheme. Third point, digital circuits are less sensitive to physical effects such as vibration and temperature. Coming on to the fourth point, compression of large data signal is possible only in digital communication. Fifth, storage and signal multiplication is easier because of advanced DSP techniques and digital computer system. Now coming on to the sampling process. In sampling process, the continuous analog signal, that is denoted by MT, is converted into digital analog signal taking at sampling instant t equals to nts. Here your continuous signal, which is represented as MT, is sampled, converted into your discrete analog signal as mnts. Here we consider a unit sampling. So Ts is equals to 1, that is equals to Mn. Here T represent your continuous time, whereas your N represent discrete time. Now considering any arbitrary signal Mt, here we consider any or message signal which is in continuous form. After sampling we will see in discrete form it is denoted by M del t. In sample signal, the corresponding sequence are uniformly spaced in time. So the sampling instance, that is your Ts, 2Ts, 3Ts up to so on. So we note a point. Both the signals are analog, but there is difference in time axis. Now here we consider a modulating signal MT as band limited signal or maximum modulating frequency. For example, we have considered any arbitrary message signal, that is MT. So if we see for the frequency spectrum of MT, so it will look like this, having a bandwidth limited from plus FM to minus FM. Mostly we consider positive frequencies only. So in order to convert analog signal into discrete signal, we use sampling signal ST. This sampling signal ST is called as carrier signal. So your carrier signal or sampling signal ST is represented as impulse trains for ideal condition and pulse trains in practical conditions. Now here, if we see, ideally we have used impulse train that is sampled at Ts, that is for fixed interval from plus infinity to minus infinity. While in the periodic, this is for ideally impulse train. If we talk about the pulse train, that in practical we have pulses having a bandwidth of represented as Tw. But practically we use periodic pulse train and the width of each pulse is Tw. Here we see a relation that is Fs equals to 1 upon Ts, where your Fs is the sampling frequency and Ts is your sampling rate. Now, if we consider both analog signal and unit impulse train is passed through a multiplier, and the output of the multiplier we get sampled signal or discrete signal, that is denoted by M del T. Suppose if we see we have a message signal MT. If we used a multiplier having ST, then we get the output as discrete signal or sampled signal M del T. Here we consider your ST as a unit impulse train. So we can see our sampled signal or discrete signal at uniform rate for once every Ts second is called as instantaneous or ideal sampling. So this was all about the sampling process. Now coming on to the sampling theorem. As we know that the discrete signals are generated using sampling process, and in order to recover original band limited signal, then we use sampling theorem. So in order to recover original band limited signal from its sampled version, the sampling frequency must always greater than or equal to twice of the maximum modulating frequency component, that is Fm. Here your Fs is greater than equals to twice of Fm. This is also known as Nyquist rate. Now if we consider for a baseband message signal, arbitrary message signal, that is represented as MT, and the frequency spectrum that is denoted by capital MF, having a bandwidth of FM. Here we basically consider only positive frequency. If we see the simple signal mathematically, so your ST is equals to summation n equals to minus infinity to infinity del T minus NTS, where for frequency it is SF is equals to F naught summation n equals to minus infinity to infinity del F minus n F naught. If we see over here, if n equals to 0, at n equals to 0 we get ST. For n equals to plus minus 1 up to infinity, we get TS to TS up to so on. After sampling, we will see for discrete M del T, we have sampled and passed it through low pass filter. So the work of the low pass filter is to neglect the high frequency components and to recover the original signal. So here at the receiver, LPF is used with cutoff frequency, that is FM. So if LPF will remove the high frequency component, then we will get our recovered message spectrum. So this was all about the sampling process and sampling theorem. In the next session, we will discuss about the PAM. Thank you.